We have seen the notion of an exact differential equation. We have seen how sometimes you would be able to find what is called an integrating factor, which can multiply an differential equation and make it exact. And we have seen the prescription for finding such an integrating factor if it's a first order differential equation which is also linear. And we've also seen how first order differential equations, even if they're not linear, can sometimes be solved with the help of clever transformations, right? So in this lecture, so we will look at how sometimes differential equations appear in disguise. So apparently they look to be intractable or very complicated, but some thought reveals that they are in fact of a familiar type, right? So here also we will uh, use this lecture as a sort of a bridge between first order equations and second order equations. We look at a class of second order differential equations which will be seen to be basically effectively first order differential equations, right? So which can be solved with the help of first order differential equation techniques effectively, right? So that's the content for this lecture. Let us start with an example of a differential equation which is written in terms of differentials of x and y. So you have a differential equation y squared dx plus 3x minus y dy is equal to 0, right? So naturally we would like to write it down as this derivative dy by dx is equal to y squared divided by 1 minus 3xy in a bit to bring it to one of the standard forms that we are already familiar with. Clearly this is a first order differential equation. The highest order of the derivative is just 1 dy by dx. Therefore it's a first order differential equation, but we see that it's a nonlinear differential equation. So because of this appearance of y squared and the complicated function of y appears on the right hand side, so it looks like this is a hard problem, perhaps an intractable problem. However, some thought reveals that in fact this problem, it can be turned on its head, literally so. So that in fact you should think of this as a differential equation in x. So if you write down dx by dy, it is 1 minus 3xy divided by y squared. And now immediately you see that this equation is first order for sure in x, but also it's linear in x. So now in fact you can go ahead and bring it into the standard form, dx by dy plus 3 by y times x is equal to 1 over y squared. So you see this is in the form, the derivative plus some function of y, which is the independent variable, times x equal to some other function of the independent variable on the right hand side. So it's an inhomogeneous first order linear differential equation. We know how to solve such differential equations. So the first step is to find the integrating factor. So the integrating factor in this case turns out to be rather straightforward to compute. It's just e to the power integral 3 by y dy. So integral 3 by y dy is 3 times log y, which is the same as log of y cube. So e to the power log of y cube is just y cube. So very straightforward. So the next step is to go ahead and multiply throughout the differential equation with y cube. So you have y cube dx by dy plus 3 times y squared x is equal to y. So although we have written down the prescription to find out the answer, the final solution for a first order differential equation which is linear, it's still useful to work it out step by step. So work out the integrating factor, multiply throughout, and then explicitly you will see that the left hand side becomes a perfect derivative, right? So in this case we see that it's the derivative d by dy of the function xy cube. So and the right hand side is very simple function, is just equal to y, and then from here it's just a matter of integrating the right hand side function, which in this case is completely trivial. So it's xy cube is equal to y squared over 2 plus c. So therefore we can go ahead and write down the solution as x is equal to 1 over 2y plus c over y cube, right? So the solution is obtained in as with x as a function of y in this case, right? So the moral of this exercise is that we should, when we are confronted with a differential equation, we should try to, bring it in, tweak it around and see if there is some, a form in which it's more suitable for investigation, right? So the simplest thing is to see if which one of the two variables should be treated as the independent variable and which of them is to be treated as a dependent variable. Okay, so an apparently hard problem is, with the help of us, a closer look is revealed to be just a first order linear differential equation. Okay, so now we will enter our study of second order ordinary differential equations, it's in a gentle manner, right? So we will look at a bunch of cases which are special cases of second order differential equations, but which will be seen to be effectively first order. Okay, let's look at the first type, which is when you have, the variable y is missing. So we're looking at a differential equation of the form d squared y by dx squared is equal to a function of only x and dy by dx. So there is no y which appears on the right hand side, and when you have such a form, right, a simplification ensues if you can make the substitution dy by dx is equal to z, then this equation becomes dz by dx. So the left hand side is just dz by dx, which is equal to f of z comma x. So dy by dx, in place of dy by dx you have z comma x, and so immediately you see that now this is a first order differential equation in z, right? So assuming that f is not some extremely violent function, perhaps there is a way to solve for this, right? So we will be able to write down z in terms of x, z as a function of x. If we can do it, then we are still not done, right? So presumably this will give you one free constant, right? So and then one more integration is involved, and therefore you will end up with two free constants. So that's how the characteristics of the second order differential equation comes in. There is going to be two free constants in the end. So because the ultimate answer is to be written as y as a function of x. So let's look at an example. So suppose we are interested in solving for this differential equation d squared y by dx squared is equal to x squared times dy by dx the whole squared, and I'm giving two conditions, y of x equal to 1 is equal to 0 and dy by dx of x equal to 1 equal to minus 3, right? So if I put in these two conditions, then this will eliminate the two free constants which will come out. So according to the prescription given, we must introduce the substitution z equal to dy by dx. So the differential equation becomes dz by dx is equal to x squared times z squared, now which is a separable differential equation. It's a first order separable differential equation. So you have 1 over z squared dz is equal to x squared dx, which can be integrated, and we have minus 1 over z is equal to x cubed divided by 3 plus constant. So but we have this initial condition dy by dx of x equal to 1 is equal to minus 3. So when x equal to 1, z is going to be minus 3. So so this means that this constant is, so in other words, so you can just remove this constant doesn't count. So you have z is equal to minus 3 over x cubed, right? So if you put this constant to be 0, then you see that when x equal to 1, z is equal to minus 3. So it's just the derivative dy by dx is seen to be minus 3 over x cubed. One more round of integration, and then we get y is equal to 3 by 2x squared, and then there is another constant c2, which I have already put in this condition x equal to 1, when y of x equal to 1 must be equal to 0, and you can check that if you put x equal to 1, 3 by 2 minus 3 by 2 is 0, and so you can implant this directly into the original differential equation and check that indeed you got the correct solution. Okay, so this is one type of second order differential equation, which is actually a first order differential equation. There's another type which I will describe now, which is when you have a missing variable x, right? So here d squared y by dx squared is going to be of the form f of dy by dx comma y. So earlier we had, y was missing, right? You had dy by dx and x on the right hand side, but now you have x is missing. So you're allowed to have dy by dx and y. It can be a function of these two, and this two can be considered or treated as a first order differential equation. So with the help of the same substitution, but with a slight modification, right? So we seek a solution of the form dy by dx. This is to be treated now as z as a function of y, not as a function of x like we were doing earlier, right? So what we do is we use the chain rule and write this as d squared by dx squared is actually, it can be thought of as dz by dy times dy by dx, so which is equal to z times dz by dy. So you want to completely eliminate x from this, because the right hand side there is no explicit dependence on x. So now you see that you have a differential equation z times dz by dy is equal to f of z comma y. So this is a first order differential equation in z, with respect to y, which can be solved. Once you have found z as a function of y, you have to do one more integration, dy by dx is equal to z of y, and then you can at least formally write down y as a function of x. Okay, let's look at an example. Consider a part which is actually a familiar example. We have all seen this, and this very trick has perhaps been used by us. So consider a particle of mass m moving along the x-axis under the force f of x. So then the equation of motion is m times d squared x by dt squared is equal to f of x. So here we should not confuse the notation x here and the x here. So here I am using x and t like is standard in mechanics. X refers to distance and t refers to time. So t here is the independent variable and x is the dependent variable. So you see on the right hand side what I have called f of dy by dx comma y, here is f of just x. So this y role is taken over by x here. So in fact the equation, the example that I am considering is even more simpler than the general case that I have given here. So this is a special case of the special case where the right hand side is purely a function of the dependent variable alone. There is no dependence even on the derivative, right? So I have m times d squared x by dt squared is equal to f of x. So it is convenient to work with velocity, right? So the point is that this substitution is really like thinking about it in terms of velocity. V is equal to dx by dt. And so now comes the clever part of this trick, which is to write this differential equation as m dv by dt is equal to f of x will not do, but you have to realize that this m dv by dt is the same as m dv by dx times dx by dt. So in fact you can think of this as m dv by mv times dv by dx. So velocity as a function of position. So time is eliminated entirely, and so you see you have mv dv by dx is equal to f of x. So if you integrate both sides, you get half mv squared is equal to integral of f of x dx plus constant, right? Which is seen to be in fact nothing but the statement of the conservation of energy. There is a kinetic energy plus potential energy is equal to a constant. So there is this negative sign, which comes in because work done by the force and work done on the body. There is this sign convention involved. But basically the point is that you have kinetic energy plus potential energy is equal to a constant. There are many problems where we have directly used this principle, but if you analyze this from the point of view of a differential equation, you see that here there is this trick used where we convert a second order differential equation into an effectively first order differential equation and solve for v in terms of x, right? So you need explicitly what f of x is to be able to go one more step and to write down x as a function of t, right? Which is possible only if the function f of x itself is known and if the integration is possible. And sometimes it can be extremely messy, but the general prescription is available, right? That's all for this lecture. Thank you.